Okay. I tried to draw this very slowly and carefully so that things would be nicely aligned. But I didn't. I failed. But you get the idea, all right? If you look at this and you look at this, you'll notice that they're very similar. The only difference is that we've added these circuits here. And this is the first time you're seeing a circuit with multiple op amps. There are, in fact, 3 op amps here. So if you were building this as a circuit, right, you would be having to plop down 3 different op amps. Does that make sense? All right. Once again, you are faced with a circuit. You haven't seen it before. You're asked to determine what it does. And again, just use the rules of op amp. Only now you're going to have to apply the rules of op amp to each one of these operational amplifiers. This here, again, or this one here, they're the same. We've seen this circuit before, right? This circuit has a name, in fact, and it's called a follower. All right? I put a follower here and I put a follower there. And if you remember, a follower is a very interesting circuit because it does nothing. The output of the follower is the same as the input of the follower. So we could go through that entire derivation again, but the bottom line is that this voltage here and this voltage here will be tracking the respective inputs. So I could call this, I'm going to call this V3, and I'm going to call this V4, all right? But in fact, we can say that V3 is equal to V1, and V4 is equal to V2. It seems like not a lot has happened here, all right? But it turns out something has happened when we get to the application that's very useful, as far as the fact that you'll notice that no more current is flowing into the system, right? The system has somehow been blocked, right? That's what these followers do. They have this teleportation-like quality that will be useful to us later. But currently, from a math perspective, very little has happened. So that's what this stage does, and that's what this stage does. And finally, we have this circuit. Now, this circuit is familiar to us because it is, of course, the difference amplifier. It's the same difference amplifier. And the same math applies as before, right? I have a voltage here and I have a voltage here, and I would run through the exact same thing again. And I would get, for this stage, that V out is equal to R sub B over R sub A times V4 minus V3. Right? That is the equation for this stage here. And we could work it out again, but it would be the same. But we know what V4 and V3 are in terms of V1 and V2. And so therefore we can say V out is equal to R sub B over R sub A times V4 V2 minus V1. And this is now the equation for this circuit, which sure seems a lot like the equation we had before. It doesn't seem like too much was accomplished, except we've added these additional stages here, which do have a real application, but apparently not much of a mathematical implication. All right, one more step. to get to instrumentation amplifier, right? These are little steps. We did difference amplifier, then we just added this, did nothing to the math, did nothing. All right, let's do one more. Yes?
What is the real world application of using a follower? I guess you can combine digital signals.
Okay, what? In this case, I don't know, let's say we're not exactly clear what is happening here before. Voltage dividers, thermistors, your nephew is connected to it, right? And so the problem is that we have a situation where, in fact, some of these elements can interact with what came before. Even though this current is 0, this current is not 0. And this current is not 0. So if you can imagine there's a voltage divider here and then another voltage divider. We went through that example where it's not two voltage dividers anymore, is it? It's some other circuit, right? And so it's not that it's not manageable, but I would like to live in a world where I can just take a difference amplifier and I can just drop these points in, measure the voltage, and not interfere with anything that came before. So that is at the high level. When we get to specific examples, this idea will really crystallize. And I hate leading with like the derivation before the uses, but in this case, it's just the way I want to get to instrumentation amplifier, and then all of a sudden, like magic, I'm going to start giving you all this stuff for free. All right, but that's why it's not exactly the same. All right, here's the next circuit. If you've been following the progression of what we've done, it's, slightly more complicated, right? And once again, as I asked before, if you hadn't seen the circuit before, if you were told to derive it, it might seem like a lot, right? But just use the rules of op amp and you get rid of the op amps. And once you get rid of the op amps, all you have are resistors, right? So what are the rules of op amp? Well, this current here is 0. This current here is 0, right? Same thing here, I'll just draw it. First rule of op amp, right? Second rule of op amp says that when you have negative feedback, the V plus is equal to the V minus, right? That's the second rule of op amp. Now notice we have different V pluses here and different V minuses here, right? So in this case, this V minus is going to equal to this V plus. And in this case, this V minus is equal to this V plus, right? These are different, right? So we need to just keep that in mind, right? And that's it. There's no more rules of op amp, right? Isn't that interesting? And so what do we have left after this, right? What are we going to do? What are we going to do now? Now that we've gotten rid of the op amps, we're just left with this. What equation is left to us to use? I know you know the answer. I'm just going to wait for you to say it. Ohm's law. So let's do Ohm's law. All right. All right. Okay. I'm going to apply Ohm's law. I'm not going to focus on this part of the circuit because we sort of know something about it, right? I want to focus on this part of the circuit here. And I recognize that this is a little bit odd or intimidating, right? If you haven't seen it before, right? Just like the Wheatstone Bridge was odd and intimidating because of the structure, right? But I'm going to show you not to worry. I'm going to be interested in writing Ohm's law. So whenever I'm thinking about Ohm's law, I'm thinking about currents, right? So I have a current here, I have a current here, I have a current here, right? Those are my currents. Here, here, and here, right? Those are all places I could write Ohm's law on. Right? Remember, when you have a hammer, right? Everything's like a nail, right? When you have Ohm's law, you're just going to write Ohm's law everywhere. But you'll notice something here. How much current is flowing down this line? I guess I missed out. I should have drawn it to both terminals, right? 0, 0, right? How much current is flowing down this line? Nothing. There's no current flowing down this line. There's also no current flowing down this line. That means that all the current flowing here, none of it can turn this way. It all has to keep going, right? So if it's 10 taxicabs per minute, it's 10 taxicabs per minute, and it's still 10 taxicabs per minute. If this is 2 milliamps, that's 2 milliamps, and that's 2 milliamps. So these are all the same current. I don't need to label it as IR2, IR1, and IR2 again. It's the same current. So now I'm just going to write Ohm's law for this current. Okay. I'm first going to do Ohm's law from here to here. And I can do that by combining these resistors using our rule of resistors in series, right? Using an R equivalent. And as we described, when we say R equivalent, we mean R equivalent from the perspective of Ohm's law. And that would look like this. You would say that V do I want to do it the other way? All right, we'll do it this way. I'm going to reverse these. Let's go up. I think it'll be a lot easier. Because I want to write Ohm's law this way. Not that it would have been hard the other way, right? But let's write it this way. So I'm going to say that V4 minus V3 over, and now I have to add 3 resistors in series. So that's actually going to be 2 R sub 2s plus R sub 1. Now perhaps you're wondering why is the R sub 2 here twice? Because I chose it to be. I said that if this is 10 ohms, that's 10 ohms, right? That's just the way I designed it. So now I have this is equal to this current. I'll just write it here, I. All right, that's Ohm's law applied once. Now I'm going to apply Ohm's law again. And I'm going to apply Ohm's law from across this particular resistance. This is one of those moments, right, where the professor's working derivation. If you don't know where I'm going, all this, don't feel like that. I wouldn't have done that. Maybe you wouldn't have, okay? But I'm motivated because I know where I want to end up. So I'm going to say that this is equal to, because it's the same current, I'm going to write the voltage from here to here. What is that voltage? Well, if you think about it, this voltage here is V2, right? V2 shows up here. So this is V2. Right? V2 is right here. And what's here? V1. So when I write Ohm's law here, I'm actually going to write V2 minus V1 over R sub 1. Do you guys see that? Why the V2 and the V1 suddenly appeared in this equation? Should I talk it through again? Or is it clear? It's clear, right? The V2 gets, by the rule of op amp, shows up here. And the V1, by the rule of op amp, shows up here. And therefore, I get V2 minus V1. Now, when I rearrange these, I can actually say that V4 minus V3 over, oh, let's do it this way, is equal to V2 minus V1 times 2R sub 2 plus R1 over R sub 1. So this difference here is equal to this difference times a number. Right? So if this was 1 and 0, right? And these right? So if we had 1 and 0, and let's say these resistors are all 1, so we have 2 plus 1 is 3 over 1, 3, right? We'd have 3. times 1 minus 0, or 3 volts. That is the calculation that this stage is doing. So that we have a situation where we have inputs here, and then they show up here, and it's the same difference as before, but just a little bit bigger. It actually feels a little bit like a difference amplifier, doesn't it? But we still have a difference at the end of it. Final step. V3 and V4 are the inputs to this amplifier. So I can use the difference amplifier equation, which I'm going to put over it, and I'm going to say that V out is equal to R sub B over R sub A times, remember V4, this is V4 and this is V3, right? These are the inputs to the difference amplifier. So I'm going to say times V4 minus V3. Okay. And finally, and this is the last step, I'm going to combine this and this, right? Because I know that V2 and I know that V4 and V3 are this, right? I mean, this term here is in here. And so therefore, I'm going to say that V out is equal to V2 minus V1 times 2R2 plus R sub 1 over R sub 1, that's the first term, times R sub B over R sub A. Okay, and this is the equation. This is the equation for this circuit. That's the last one for today. What's that? This circuit is called an instrumentation amplifier, but there's one more step to get there. If you look at what this circuit does, I would say that this is a difference amplifier. I would say that this circuit takes the difference between 2 points on a circuit or on the body, subtracts them, and multiplies it by a number. Now, this number could be, it depends on this resistor, that resistor, that resistor, and that resistor, right? So if you actually were to compare it to the other circuits that were here, what did we gain? Maybe we gained something from the difference amplifier, right? Because I told you the difference amplifier has this issue that I don't like, where there's these sort of hanging ends. And we took care of that using this circuit here, right? In this circuit, the hanging ends were gone, and we had this equation, right? And look, it's pretty simple math, right? Look at all the work that was done here. All this work, right? I had to use 2 operational amplifiers. And as you know, that means you have to power all of them, and you got to connect them, and you got to get a resistance, and you got to get another resistance. This on its face is more complicated, more likely to fail, and makes no sense because it was all this work to produce something that these other circuits already do. And the reason we don't do extra work is because as an engineer, you have to be lazy. When you make things, there's a very high chance you will make a mistake. When you make things, you don't want to use more components than you need to use. It just is a really bad idea, right? You should, as an engineer, be using the minimum number of components you need in the simplest possible thing. And so this thing, compared to this thing, is a disaster because it adds components and it adds complexity without doing anything else. Okay, what's the setup, right? All this is a setup, right? And the setup is, in fact, that laziness wins. Let me show you why. In this circuit here, you have to pick 4 resistors, right? 4 resistors, maybe a 2 ohm, a 2 ohm, a 1 ohm, and a 1 ohm, all right? Factor that into your level of laziness, okay? You can say, I'm so lazy. Even that is a problem for me. But there's another issue. If this is 2 ohm, 1 ohm, 1 ohm, and this is 2.1 ohm, this breaks. And your circuit will not do what it needs to do. If this is 2 ohm, 1 ohm, 1.05 ohms, 2.03 ohms, this is no longer valid. So not only do you need to pick 4 resistors, you have to make sure that they're exactly right. And we'll talk about later what the consequences of them not being right practically, but mathematically it's that you don't get the output we had before, right? Which was the same as this. How about in this case? In this case, you've got to pick 4 resistors, right? And you better make sure that their values are exactly right. And, right, you have to power up these 2 additional op amps, right? More work for sure. And what about this? So what you need to understand is that inside this chip, someone already built, let's see if I can draw it, like this chip is all of this. This chip has inside of it 3 op amps, effectively, because engineers are lazy. And if I could say one option is you build a circuit with 3 op amps, power all of them, connect all of them up, don't make any mistakes, or use a single chip that has 3 op amps in it, you would rationally want to use one chip, right? And so we get all this, right, which has a benefit that that doesn't have, right, because it has these buffers in the beginning, on one chip. But I also told you there's only a single resistor here. So when you make this circuit, you don't need to pick 4 resistors. And you don't need to make sure that there is this perfect parity between the 2 pairs. You only need to pick one. This one is R1. So this circuit here, the only thing on the outside of the circuit is R1. RG, I can call this RG is equal to, could use the same thing, is R1. So not only did they build the 3 op amps for you, these terminals here are available to you to insert a single resistor. All the other resistors are fixed. Let's assume that all the other resistors are 1. If that was the case, this would reduce to, right? This is if all the resistors are 1. I'll do it in a different color. Maybe you won't get confused. V out, ooh, no, I'll do it in purple. V out is equal to V2 minus V1 times, and it's going to be 2 plus R sub 1 over R sub 1 times 1, right? So if all the other resistors are picked to be 1 ohm, then the only thing unknown is R1. And so the output is given by this equation here. If you wanted to make a circuit, for example, with a gain of 3, you would just pick R1 equal to 1 ohm. And you would insert a single resistor. In fact, any gain you want, right, this is the gain. This is the gain. Any gain you want can be obtained simply by picking a single resistor. And this is where the laziness comes in. This is the laziness. It can't be any less work. It's a single chip. You have your inputs, right? And these correspond to, this is your sort of V1, right? This was our V2. Got to power it up, no way around that. Now you get your output, and just use a single resistor. So an instrumentation amplifier is ultimately a difference amplifier, right? With the added benefit that the inputs are buffered. And we're going to leverage that, right? But the real catch is that you only have to insert one resistor instead of inserting 4. And you can say, that doesn't sound like a real benefit to me. Fine, don't do it. Make this. And make this. Right? I'm not gonna force you. Make a circuit with 3 op amps. How many things do you think can go wrong here? Right? What are your chances of finding these resistors? And by the way, how well balanced do they need to be? For some applications, within a fraction of a percentage. So you may say, I found a 2 ohm and a 2.01 ohm. Is that good enough? That's not good enough. Go back to the bin. Right? So you're spending a lot of time not just finding the resistors you want for the gain, but making sure you can balance them perfectly. Meanwhile, the next person over, 1 chip, 1 resistor, right? When they did this at the they made sure that all these other resistors here were very, very, very precise, right? They built this chip has the resistors inside of it, right? And so when they built it, they ensured that it was very precise. They're handing it to you with all those resistors very precise, and they're only asking you to pick 1 resistor. Yes. Oh, so the question is, should this be 2R2? So what I did here is I just assumed that when this came, this was 1, 1. Oh, you're right. No. It's like this. It's like this. Right? R2s come as 1 ohms. Only R1 was left open, right? And so this was a 2 times 1 over 1, 2 times 1, and then R1 and R1 were left. Now, you could say, but is that what they actually are? No, that's not what they actually are. And so what you'll see here is that there's another equation that you'll be given. But when you're given your instrumentation amplifier, you are given an equation that says the gain is going to equal to, and it's going to be some number, call it A plus R1 over R1. It's going to be something like that. It may not be 2, right? Maybe there'll be another constant here, I'm not sure, B. But in any case, you're only asked to insert 1 resistor. Just grab 1 resistor and put it in. And this is not such complicated math. Just do the math and you get any gain you want. 1, 10, 13.5. Just select the gain you want and one equation, 1 unknown, and solve for R1 and insert the R1 into your circuit. So the instrumentation amplifier is, I believe, the simplest circuit, right? It asks very little of you for what it gives you. All right? Okay, so that concludes the introduction to the instrumentation amplifier. All right, now you could say, what is it good for? I'm going to give you a couple hints. If you take these wires here on the chip, right, and you put them across your chest, on the output, you're going to see your heartbeat. Interesting. Is it, of course, I always leave little details out, right? But that's it. So do you want to know do you want to know the schematic for a heart rate monitor? This is the schematic for a heart rate monitor. The chip? Yeah. 1 chip. Yes, there's always nuance. Pick the right resistor on it. And you're going to see many other biomedical instruments where this is the schematic. That's why it's the instrumentation, because we're going to use it. It's going to be a one-stop shop for many things. We're not going to go through these derivations again, and maybe you can forget them. Maybe you don't care, right? All I need you to know, right, is that this is what it is, and this is the equation that's associated with it, or more specifically, an equation that looks like this. That's all I want you to take away from it. And armed with that, and again, it's almost like deceptively simple. Like it does so little, it seems like it does nothing. We're going to find out all the things that we can use it for. Sounds good? All right, so that's it for today. And so on, oh.